Assalamu alaikum everyone. My name is Russell Parvez. I am from Buet Tripoli 19. In this demonstration video, I am going to be talking about Cascode Amplifier, which is a topic relevant to the electronic devices and circuits course. In that course, we study various amplifier configurations like common source amplifier, common gate amplifier, common drain amplifier. A Cascode amplifier is basically a cascaded version of a CS stage and a CG stage. What is the goal of this amplifier circuit? The goal is actually to increase the gain of the circuit. Here we can see the input is given at gate and output is taken from drain. So this is a CS configuration, and this output is fed into the source of this MOSFET. So input is given at source and output is taken from drain. So this is a common gate configuration. On the left side, we have shown the basic CS amplifier with a resistive load, and this equation gives the small signal gain of this circuit. So our motivation is actually to increase the gain of this circuit more. What do we mean by gain? For example, if we have input of amplitude 1 like this minus sign indicates that we will get inverted output, a more bigger output like this. For example, if we have a gain of minus 3, then the output will have an amplitude of 3. And now our goal is, with this circuit, we actually want to increase the amplitude of the V out more. We want to get an output like this. This is our motivation for the Cascode amplifier. To analyze the gain of the circuit, we will actually use this equation. Using this equation, we can find out the gain of any circuit. We need to calculate the total transconductance of the circuit, and we will have to calculate the output resistance. In this slide, we have shown the steps to calculate the total transconductance of the Cascode amplifier. First, we need to ground the Vout terminal. See that Vout is grounded. Then we need to ground all the DC sources. See that this VDD is grounded. Also, the gate bias is also grounded. After grounding all these terminals, we need to evaluate this ratio, that is the short circuit current and input voltage. What is this short circuit current? This is the current that flows from the Vout terminal to ground. See that this RD is eliminated from the circuit as it is connected between two ground terminals. We have redrawn the circuit again. Now, to evaluate IC divided by Vin, we have replaced the MOSFETs with their pi equivalent circuits. Here we have applied KCL at node P. We can see that IC is formed by these two current components, but the actual direction of current in these two branches are opposite. So we have applied a minus sign before these two terms. Then VDS2 is replaced by VGS2. Why is that? Because the drain terminal is grounded and the gate terminal is also grounded. So we can say that this point is the same point as this. So we have replaced D with G. In the same fashion, we applied KCL in this Q node. So we got another equation of ISC. Then we replaced VGS1, that is this voltage, with V1, Vin, and VDS1 with this term. Let's look into it. D, that is this terminal, is connected to S2. So in the place of D, we have written S2. And in the place of S1, which is grounded, we have written actually G2 here. But as we flip the order of them, we have placed a minus sign here. So finally, we have achieved two equations of the same kind. So you can write this term is equal to this term. We have written this here, then separated this term in one side and the other terms on the other side. RO1 and RO2 represents the drain to source current of M1 and M2. These have significant values, so the reciprocal sum of them will give us a nearly zero value. So we need to only multiply these two terms. Using this approximation, we get this equation. Then we rewrote the first equation of IC shown in the previous page. Then we applied the same approximation that 1 by RO2 will give us nearly zero value. So we need to multiply only these two terms and we get this term. If you look closely, this is same as this term shown here. So we can replace this term with this term and finally get the final equation of IC, which is written again here. So when we take IC divided by Vin, we get the total transconductance of this circuit. And surprisingly, we see that it is actually equal to the small signal transconductance of this M1. It means that even after adding M2, we haven't seen any change in the total transconductance of the circuit. So we say that GM will remain unchanged in the Cascode amplifier. Now we will calculate the output resistance of this Cascode amplifier. To find R out, we need to calculate the total downward resistance and the upward resistance looking from the output terminal. To find the downward resistance, we added a test voltage source in the output terminal and grounded all other voltage sources like this VB and Vin. From this circuit, we will now calculate VT divided by IT ratio. This will give us the total downward resistance of the circuit. We have redrawn the circuit again here and replaced the MOSFETs with their equivalent pi circuit. Notice M1, both the source and the gate is grounded. So VGS will be 0. So this current source will be eliminated from the circuit. We have only drawn the resistor here. From this total circuit, we will now evaluate Vt by It ratio. Now we will apply KCL at node P. We can see that the current It is formed by the current in these two branches. So we have written the expression of It here, and these are the two current components. Now we need to find what is VGS2 and VDS2. VGS2 is written here. It is the voltage difference between gate and source. The gate is grounded, so we have written 0 here. VS2 remains. The expression of VS2 can be seen from here. The source voltage is actually IT times RO1. So we have written this here. Similarly, VDS2 is the difference between drain and source. The drain is connected to VT, so I have written VT here, and the source voltage we have already determined and we have rewrote it again. From this whole expression, now we will find VT and divide this whole expression with IT. This Vt by It represents the total downward resistance of this circuit, and which is our desired expression. We can see that this is quite a large resistance compared to a basic CS amplifier. Here we calculated the total small signal gain of the circuit. We already evaluated the total downward resistance. If we use a resistive load, we will replace R up with RD. If we use a current source load, we will replace R up with infinity. We have assumed that we have used a current source load, so the effective output resistance will be actually equal to R down. So we have written the expression of output resistance here. When we multiply this with the total transconductance of the circuit, we will get the total small signal gain. Here is the expression of the total small signal gain. We have assumed that both transistors are identical. We can see a significant increment in the gain of the circuit. When we used a single stage CS amplifier, the gain was only minus GM/R0. Now there is a whole square above the whole term. So there is significant increment in the gain of the circuit, which was our actual goal. We wanted to improve the gain of the circuit. We want to increase the gain of the circuit more. So we can see we have achieved it. To get the full advantage of Cascode amplifiers, we need to select the load carefully. When we use an ideal current source, the upward resistance is infinity, and the downward resistance is GM/R0 square, which we showed in earlier slides. So the total output resistance will be given by this expression, which is actually equal to the downward resistance, which is a larger value compared to a CS amplifier. So this increased R out will give us a larger small signal gain. To implement current sources, we use PMOS in actual circuits, which is known as an active load. If you use a single PMOS in the place of the current source, the upward resistance will be R0 and the downward resistance will be GM/R0 square. So the total output resistance will be given by this. As R0 is significantly smaller than this value, the output resistance will be something near R0. But we see here, even if we have added 2 transistors here, but the output resistance hasn't increased in this case. So the gain will also not increase. It will be something like a single stage CS amplifier, which is a problem for us because we have used the Cascode circuit, but we haven't achieved a larger gain. Why we have faced this situation actually? Because these two resistance values are not matching. This value is very smaller than this. If this value and this value were comparable, we wouldn't have achieved such a small value of resistance. What is the solution? We need to match the upward and downward branches resistance. So this is the final circuit. We have used 2 PMOS as loads, and this is the previous configuration. So the upward branch and the downward branch has equal resistance, so the R watt will be something like this. It will not significantly drop like that. Then we will have a significant gain value like this. There is a major limitation in this Cascode amplifier circuit. Here we have used 3 transistors, so our expected gain is minus GM/R0 whole cube, which is a very significant number, a very significant gain. But even if we have achieved a large gain, our output has a problem, that is reduced head swing. For this circuit to work fine, we need to ensure each MOSFET remains in the saturation region. And to maintain a MOSFET in saturation region, it needs to have a minimum delta V across the drain and source. So we need to ensure each MOSFET has a minimum voltage of delta V across it to be in saturation region. So Vout actually can't be 0. The minimum voltage of Vout that needs to be maintained is 3 delta V, and the Vout was expected to reach VDD, but it can't actually. The maximum voltage that Vout can reach is VDD minus 3 delta V. It means even if we have a very large signal, it will be actually clipped off at VDD minus 3 delta V and 3 delta V. It cannot actually have its full swing between 0 and VDD, which this phenomenon is called reduced head swing. So this is a major limitation of the circuit. There are ways to overcome this problem, but I am limiting my demonstration up to this. I hope I made all the points clear. Thank you all for listening to it. Assalamu alaikum.